Hello, everyone. I'd like to give you an overview to our course on resilience analytics, give you a little bit of an idea about where this topic came from in the first place, and then what's in store broadly for the rest of the semester. So first, this course was taught on campus in the spring of 2018. And it was taught by me, along with Andres Gonzalez and former colleague Shima Mohebi. All three of us were at the time in the School of Industrial and Systems Engineering here at the University of Oklahoma. And the primary source of funding for the course was from the OU President's Office and the Provost's Office in the form of a Presidential Dream Course. So the idea with the Presidential Dream Course is faculty can propose a course to teach, their dream course, if you will, and the President's Office provides some funding to bring in some speakers to help enrich the course. And so that's what we did back in the spring semester of 2018. We recorded all of the guest lectures for eventual use in an online course. And we had proposed that sort of online course in a National Science Foundation grant on resilience analytics. It was funded by the CRISP program, which stands for Critical Resilient Interdependent Infrastructure Systems and Processes. And so a lot of the motivation for how we were thinking about interdependent infrastructures, cyber-physical social systems, and so on, were really related to the research that we had done in that grant. And several of our research partners in that grant are speakers in the course. So the motivation for studying this topic in the first place, resilient cyber-physical social systems, broadly deals with the fact that society relies on infrastructure systems for daily life to get us from one place to another, to enable our lives as well as economic productivity and so on. But those infrastructure systems can be disrupted, and those can have consequences to society, to us, to those who rely on those infrastructure systems, to other infrastructure systems that rely on the ones that are disrupted, economic systems that rely on infrastructure, and so on. So there can be some widespread impacts of disruptions to such infrastructure systems, infrastructure networks in particular. Therefore, there's a need to understand their resilience, and we'll talk all about that in this set of slides and beyond. So the course title for the original course, we've shortened it to Resilience Analytics, but the bigger title for that original course was Analytics of Resilient Cyber-Physical Social Networks. So why this course title? Well, we were interested in the study of such networks from a data-driven perspective. Okay, so a lot of the tools and methods that we're going to be talking about throughout this course will be the result of data-driven statistical methods, also optimization methods, also simulation methods to describe, predict, and prescribe behavior. In analytics, of course, there are generally three flavors of analytics: descriptive analytics, predictive analytics, and prescriptive analytics. So descriptive analytics, they describe some kind of behavior, the use of statistical tools to describe behavior. For example, could be visual tools to visually depict what's going on with a process or system. We could be talking about some basic methods of statistical inference to describe what's going on with a process or system. With predictive analytics, we might be interested in predicting what might happen, maybe in the future, maybe under different kinds of conditions. Can we predict, using history, can we predict what the behavior of these cyber-physical social networks might be? And then finally, if we can describe those networks and if we can predict their behavior, then hopefully we can prescribe how we want them to behave. Okay, so with prescriptive analytics, we might try to tinker with the design of such networks to get them to operate in a way that we're interested in, to make them more resilient, for example. So what changes can we make to these cyber-physical social networks such that we can prescribe a resilient kind of behavior? Resilience, broadly speaking, is an ability to withstand, adapt to, and recover from a disruptive event in a timely manner, right? We talked about these disruptions that might occur to these networks. We're interested in trying to build into these networks resilience, and here's what resilience means: an ability to withstand, adapt to, and recover from a disruptive event. Cyber-physical systems are the integration of computing elements and physical components. You might imagine you interact with these kinds of systems all the time, where there are physical kinds of elements, and those physical elements are in some way governed by some sort of cyber element. And naturally, we use these things, we use these systems. So there's a human element associated with these kinds of systems. And finally, a lot of these systems are network structures. They have network properties, which we're going to talk about in more detail a little bit later on in the course. But it just makes sense for us to primarily focus on networks for these kinds of systems. So, generally speaking, with cyber-physical social systems, they refer to engineered systems with some concepts of intelligence, that is some sort of maybe predictive behavior, trying to understand user behavior to try to perhaps better function as engineered systems. They might be built with sensors in mind, so there's some sort of understanding about how the engineered system is being used, and perhaps it can then adapt through intelligence, adapt its behavior. And then finally, there's oftentimes robotics involved, some sort of physical manipulation going on with these engineered systems. It might be driven by those intelligent systems and those sensors and so on. A lot of different applications associated with cyber-physical social systems. For example, in healthcare, healthcare has benefited these days with, for example, robot-guided surgery. So there are some sensors in the OR environment, operating room environment, that give feedback to medical staff, and then robots are often used for precision sorts of surgeries. There's naturally a human element there. There's naturally the social aspect of those cyber-physical systems, but there's a strong relationship between physical elements and computation. Autonomous vehicles, naturally those things operate to a large extent on their own with some sort of human interaction with that operation. And there's a lot of cyber-physical elements associated with collision avoidance. Sensors that detect how far away different objects are, that would automatically govern speed of the vehicle, automatically stop the vehicle if there's an encroaching element in the driving view of that vehicle. And then finally, with smart cities, a lot of our infrastructure systems, buildings, and so on, have cyber-physical elements where there's sensors that monitor a variety of characteristics about buildings and make adjustments to change comfort level, to change safety, and so on. Okay, so there's these sort of cyber-physical social systems exist all around us, but we're going to primarily focus on infrastructure systems, and primarily infrastructure systems that are described with network sorts of structures. The Department of Homeland Security has identified 16 systems, broad categories of systems, sectors that are deemed to be critical infrastructures. We'll talk about those and focus primarily on 4. And you can find out more information, and some of the graphics coming up are derived from the Department of Homeland Security. So one such critical infrastructure sector is the chemical sector. Okay, so this is a sector of the U.S. economy that's relied upon heavily by society, which manufactures, stores, uses, and transports chemicals. Disruptions to the components in the chemical sector could have large-scale effects, particularly in like the physical disruption, the physical perhaps explosion of these kinds of facilities could have wide-ranging effects to the communities around those facilities. The commercial facility sector, this is a sector that essentially describes public use facilities, okay? Shopping facilities, buildings that house companies, businesses, and so on. Okay? These are oftentimes very visible infrastructures. Thinking back to the attacks on September 11th, 2001, the attackers attacked very visible commercial facilities, right? That was their intention, to attack those very visible infrastructures that would obviously have economic consequences, but they were also just very visible, the tallest buildings in the country. And that wasn't done by accident. That was done quite intentionally to disrupt those particular kinds of commercial facilities that are very visible to society. Another sector, the critical manufacturing sector, manufacturing certainly of key components in the U.S. is quite vital, particularly certain metals that are perhaps unique to the U.S., perhaps unique to elements of a supply chain that are perhaps used in a variety of applications. Those sorts of infrastructure sectors, or those sorts of companies, those sorts of facilities that house those very unique manufacturing facilities are vital to be protected. Any sort of disruption can have wide-ranging economic consequences, perhaps not necessarily direct impacts to society, but certainly to the economy. If a particular manufacturer of a particular kind of metal is shut down or can't distribute, that could have wide-ranging effects in other elements of a supply chain, which could eventually have economic consequences to us as a society. Perhaps certain goods aren't on the shelves because they can't be produced. Another infrastructure sector is the dams sector. So these are infrastructure systems that retain water, of course, but then also have power generation capabilities in a lot of circumstances. Some of them are aging. Some of them are in need of repair, and those repairs, if not fulfilled, could have a substantial impact on surrounding communities surrounding these dams in terms of flooding, in terms of power generation, and so on. The defense industrial base sector is another sector of another critical infrastructure sector that provides goods and services to the armed forces. The emergency services sector, which is important to this course. We'll talk about this a little bit later on. The emergency services sector provides, emergency response, preparedness for disruptive events, response to those disruptive events in terms of medical care and so on. The financial services sector, naturally, all of our economic activity is governed by currency and so on. And financial services are an important part of just daily economic life. Food and agriculture sector oversees the production of crops, regulation of crops, and then entertainment to the extent that we have, food production and so on. Accounts for roughly 1/5 of the nation's economic activity. So a major part of the U.S. economy deals with food and agriculture. And so naturally it's vital. Government facilities sector, so essentially just government, okay? The operation of government is itself a critical infrastructure. Healthcare and public health sector, another important critical infrastructure sector, especially when it comes to just maintaining the health of U.S. citizens, providing healthcare, managing pandemics, and so on. The information technology sector, keeping our cyber infrastructure safe when it comes to elections in the government sector, or when it comes to just services that are provided to companies to keep your information safe, to Wi-Fi connectivity in your home and elsewhere. Nuclear reactors, materials and waste sector. We don't have a tremendous number of nuclear facilities in this country, but those are considered to be a critical infrastructure, particularly in their protection. But there are 4 sectors in particular, so those are the previous 12 that we discussed out of the 16. There are 4 in particular that are of interest to us. And why is that? Well, 1, they are described by networks. And 2, they're relied upon by essentially all of those other sectors, in addition to us as citizens. The first is the communication sector. So this enables communication across the United States and beyond, whether that is telephones and wireless to the internet and so on. And of course, you can imagine that especially, if we're talking about telecommunications or if we're talking about the internet, though that is the connection of different nodes by different links. Okay, we'll talk more upcoming in the course about how we can represent some of these different infrastructures as networks. But that it should come to mind that this would be a network kind of system. The energy sector. So here we're talking about pipelines for oil and gas, but also electric power production and distribution to homes. Naturally, again, if we're talking about pipelines, those are networks. If we're talking about power grids, those are also networks. So here we have a highly networked kind of system. The transportation system, this would describe highways, railroads, waterways, and airways throughout the country. And naturally, you can think of inland waterways, you can think of railroads, you can think of highways, and frankly, even air traffic. You can think of all of those as networks. And then finally, water and wastewater systems. So here we're talking about the conversion of wastewater into something healthy for the environment, or at least not too toxic for the environment, but then also the transport of potable water to our homes. And again, if we're thinking about water flowing in pipeline, that's a network. So let's think about then disruptive events and how disruptions might impact those different infrastructure systems. And let's think about a disruptive event as just the initiating event, okay, that leads to the disruption of whatever these networks might be. So those could be in the form of a malevolent attack, some sort of attack with intentional disruption. We could be talking about a common cause failure or accidents or natural disasters, more likely natural disasters. So malevolent attack. Malevolent refers to having or exhibiting ill will, wishing harm to others, or malicious. And so you might imagine with a lot of malevolent attacks, you might in your mind think of a 9/11 kind of attack, where loss of life is a major goal. But that's not necessarily what we see on a daily basis. And of course, that was a rare event. These are, in terms of large-scale disruptions to infrastructure networks, those that take lives generally are quite rare. But what are not rare would be cyber attacks. Those happen all the time. Okay, cyber attacks that could have disruptive effects on our infrastructure systems. Here we see a recent story, not too recent, but nevertheless, where a gunman attacked a power station, shot up a power station in California to disrupt the electric power grid. Here's a cyber attack story where hackers tried to gain access to the power grid. And here's another story about hackers in another country not hackers, but perhaps a disruption, a malevolent attack in the form of an EMP, high altitude EMP, which essentially is a nuclear blast up in the atmosphere, which could have detrimental impacts on our electric power and communications networks here in the US. With failures, there are just, failures just generally would describe common cause disruptions, okay? A result of degradation, could be the result of just randomness. It could be that, that there's just a random outage that just occurred just because it did, just because it was random. There was no ill will involved. It could just be a failure that was just random. Okay. So the field of reliability engineering has long, for decades, studied the idea of degradation and failure. Okay. And so here's a picture of a bathtub curve, which again is a long-studied graphical depiction of failure rates over time. So early on in the life of a system, we have a failure rate that's decreasing. Okay, so we're describing early on decreasing failure rate. Failures that occur just due to burn-in, just starting up the system, something may be a little haywire, and failure occurs early on. Okay, but as time goes on, if the system operates, then as time goes on, it's probably going to keep operating for a while. There's probably not going to be that early failure. And so we're going to experience decreasing failure rate over time. Then, for a certain period of time, for the use of a processor system, we'll see a useful life. That's just described with a constant failure rate. So, after burn-in, this processor system is operating, this infrastructure network is operating. It'll probably operate for a while before we experience some sort of degradation. So it has a constant failure rate, and that constant failure rate is probably pretty low. And then after time, the processor system wears out, and we start to experience an increasing failure rate. And so here we're seeing where degradation has caused failure to be more likely. And so to try to understand this curve, try to be able to prevent degradation to the point where wear out and an increasing failure rate occurs, that's one key area of study in reliability engineering. And by the way, this bathtub curve describes us as humans, right? So early on, there could be some complications, which could lead to some disastrous results. But after we live for a while, we're probably good. up until, things start going south. But let's not think about that, okay? Let's just think about failures of cyber-physical social networks. So for repairable systems, we can perform maintenance on these things. We can try to change what that curve looks like. For these infrastructure networks, we can figure out how to try to maintain, try to invest, to try to prevent disruptions. Okay, in the form of preventive maintenance. However, we haven't really made these investments, right? This sort of preventive maintenance takes a lot of money. We have a lot of infrastructure across the United States. This is a big country. And so a recent report card by the American Society of Civil Engineers rated our America's infrastructure with a D+, so not too strong. And that's an overall score, but let's take a look at some of these infrastructures in particular. So what do we see? Bridges, C+. Ports, also C+, though getting better. We've put some money into ports. Our school infrastructure, woeful, but improving. Transit, our mass transit infrastructure, D- and getting worse. So you can see where, really across the board, there's a lot of investment that's needed to maintain our infrastructure systems to try to stave off some of those just common cause failures. These aren't even the result of natural hazards. We're not even talking about malevolent attacks here. We're talking about the potential for just common cause failure. Though we're also talking about a higher susceptibility to natural disasters. Okay, you take an energy infrastructure. You take a power grid that potentially has a score around a D+. You combine that with an ice storm in Oklahoma, and that could have really adverse consequences, long-term power outages. So while I'm talking about failure, and while I'm talking about common cause, just failure due to degradation, this kind of degradation could also be exploited by another kind of disruptive event. With respect to accidents, this isn't something that we see a whole lot, though part of the field of reliability became popular because of the Nuclear Regulatory Commission and problems with nuclear power plants, which were primarily driven by human error. Nevertheless, those are certainly possible. And there was one case here in Oklahoma back nearly 20 years ago where a barge ran into an I-40 overpass in eastern Oklahoma and took down the overpass for several weeks and also killed 14 travelers. So these sorts of events can occur and can affect cyber-physical social networks, perhaps not so likely. And then finally, natural disasters. These are the ones that we hear about a lot more often, where, and also we're seeing where these kind of events are getting stronger yearly. Every year it seems that we pass milestones in terms of the economic consequences of such disruptive events. Okay, and we see a few here in recent times. Okay, highly disruptive earthquakes, like the one in Japan, and like the one that could happen next. It's said that the Pacific Northwest is a hotbed for seismic activity. Perhaps the next big one could be up in the Portland, Seattle, Vancouver area. also in the middle of the country, the New Madrid Fault Zone, seismic zone, could have high consequences if an earthquake occurs in the middle of the country here in the U.S. And of course, as I mentioned, they can disrupt. These kinds of natural disasters can disrupt lives. They can take lives. They can disrupt lives. They can disrupt our infrastructure system. But they're also very costly in terms of recovering from them, but also the consequences associated with a lack of productivity. If we have an electric power outage for a week, well, there are certain businesses that can't stay open. There's certain economic productivity that cannot occur as a result of that. And so what are we seeing here? Well, with transportation infrastructure in particular, we can see flooded streets. With earthquakes, we can see cracked pavement that have to be fixed, structurally unsound bridges. After an ice storm that we might see in Oklahoma, for example, we might have debris on thoroughfares that has to be cleaned up and eventually removed. And that can be costly and time intense. With respect to our water infrastructure, we could have broken water lines easily. We could have flooded wastewater drains, which have to be repaired. With electric power, with the energy sector, we may have down power lines that could take weeks and weeks to fix. We especially see that in Oklahoma with some of these large-scale ice storms. We could have flooded substations, which can have a detrimental impact on power distribution. And so for all of these kinds of disruptive events, whether it's a malevolent attack, whether it's some disinformation attack, whether it's just a natural disaster, we care so much about what happens to the physical infrastructure. Well, it's not, the physical infrastructure didn't sprout and exist on its own, okay? That street out here that you drive on to get to the grocery store, it didn't just sprout out of the ground. It exists because you need it to exist, because we all need it, because society, our community, needs that infrastructure to exist. So do we really care what happens to physical infrastructure? Well, on its own, no. But whenever it impacts us, yes. Whenever it impacts the economy, yes. Whenever it impacts health and productivity, yes. So the physical infrastructure on its own, perhaps not so important, but the impact that it has on us, very important. So that's why we study this. And that's why it's important to kind of break down, try to separate the different elements of cyber-physical social networks. So with respect to cyber-physical social networks, I consider these to be three integrated networks together. And this was the focus of the NSF grant that I mentioned earlier. So we have physical infrastructure networks. These are used to be referred to as lifeline networks. Electric power, okay, water, transportation. Those are the three major ones that we're going to talk about in this class. Those are those physical manifestations of infrastructure that we interact with regularly. And who's we? Well, those are community networks. So it's a different network of people that interact with those infrastructure networks. We drive on those streets. Our apartment building needs that electric power and so on. Okay, so those are communities of neighborhoods, families, workplaces, and so on. So whenever physical infrastructure are disrupted, that has an impact on community networks. Okay? So there's an interdependence, not only among the infrastructure networks. Okay, it could be that the water distribution facility requires electric power to operate. It could be that electric power requires the distribution of water to cool the electric power generation systems. So those might be interdependent, but then also there's this interdependent element with the community on top. Okay, the community depends upon the electric power, depends upon water, and so on. And then finally, after a disruptive event, service networks might be engaged. What do we mean by this? Well, this could be restoration crews that engage with the infrastructure networks after a disruptive event. Those work crews that go out and restore power lines after that ice storm. But those service networks could also engage with the community after a disruptive event. Okay, it could be in the form of emergency response. IMSA showing up for an emergency. That could be the result of not having access to some of those physical infrastructures. Okay, electric power is down, therefore a particular piece of medical equipment isn't operating. Therefore, emergency responders need to attend to somebody. Or it could be that emergency responders attend to someone who was also disrupted by that same disruption that affected the physical infrastructure. And by the way, those emergency responders, the way that they respond to the community is through that infrastructure network. For them to leave their depot to arrive at a patient, to arrive at a person in need, they have to traverse a transportation network. If there are limbs or if there's flooding on that transportation network, they can't meet the needs of the community. Okay? So these service networks are interdependent with the community and with the infrastructure networks themselves. Okay? So it's not just the physical infrastructures that are interdependent with each other. The community relies on those as well. Service networks engage with both. Okay? So let's keep that in mind throughout the semester. How do we measure performance of these things? Okay. How do we measure the performance of infrastructure networks? Well, we'll talk about that a little bit later on in the semester. How do we measure the effects of a disruptive event? Do we measure that in the physical infrastructure? Right? Do we measure that in terms of the length of time that the power outage occurred? Or do we measure that in terms of the effects on the community? The number of days that the community didn't have power, right? These are two different perspectives to think about. And different decision makers might think of those in different ways, right? Someone who's in charge of a utility, they are primarily interested in regaining homes without power. But for those people in those homes, each home may not be the same. There could be other ways to describe these disruptive events that go to a more community level. So we'll talk about some network characteristics that might be good for describing the effects of a disruption. So those network characteristics could be very graph theory driven. They could describe the structure of the network itself and what the impact of a disruption is to the structure of the network. But it could be that we don't care so much about the structure of the network, we care about what the network does. We care about the flow that would be expected to traverse that network. Okay? Do we care about describing a disruption in a rail network by now the updated shortest path in the network? Well, that's a very graph-driven measure. Maybe what we care about is the disruption in flow along that rail network. Maybe that's really what matters. Does it matter that this particular stretch is out and therefore it changes how we describe the network, the graph itself, the physical embodiment of the network? Or does it matter that we can't push flow from one origin point to some destination point that may need that flow of commodities in that rail? network. Okay. So it's important to think about. What are the network characteristics associated with a grid disruption? What are the flow characteristics? What are the impacts to the community of that flow? Maybe that's a better measure. Maybe a better measure is the impact of that flow to a particularly vulnerable community. Okay. So there are a lot of different perspectives we can take whenever we think about the effects of a disruptive event. What are the impacts on society? So we talked a little bit about resilience earlier. The term resilience refers to, here's another definition from the DHS. The term resilience refers to the ability to adapt to changing conditions and withstand and rapidly recover from disruption due to emergencies. Okay, that's a Homeland Security focused definition, but it broadly captures what we discussed previously. The ability to withstand the initial impact, to adapt to that impact, and eventually recover from that impact. We can try to describe graphically the notion of resilience. Here's one way to do so. If we think about performance, whatever that performance measure might be, and this could change from system to system, and there could be multiple different measures of performance we might be interested in for a particular system. But let's think about phi as being that measure of performance. And let's say it changes over time. So there's some initial level of performance at time t0. And then a disruption occurs at time te. So prior to te, there was some stable state at which the system was performing, the network, let's say. And then after that disruption, there's some drop in the performance at time down to time td. So let's say it bottoms out at time td. So we experience a system disruption during that time. So in my work, I tend to refer to that as vulnerability. Okay, how vulnerable is the network? How much is the performance of that network disrupted after a disruptive event? Okay. And then there's some disrupted state for some amount of time, and then restoration, recovery occurs until time TF. We describe that with recoverability. Okay, I'm a systems engineer. I like to think about properties of a system in terms of ilities, reliability, maintainability, and so on. And so I consider the two main dimensions of resilience to be vulnerability and recoverability. Okay. Vulnerability describes the extent to which performance drops. Okay. To what extent can a system, a network, withstand the disruption? And then to what extent can it recover in a timely manner? That's recoverability. Out past time TF, and there's some sort of stable recovered state where that stable recovered state may not be the same as it was at time T0. It may be better, it may be worse, but it's at least some stable state. Okay. So this is a graphical depiction for resilience that I use in a lot of my work, and it's very similar to several others that are used. For example, this is the resilience triangle. Okay, it's used, had its original use in some civil engineering applications. Okay, so here we're describing resilience as a function of robustness. Okay, to what extent can we stave off a reduction in performance, and then how quickly can we get back to that previous desired state? That's called rapidity. Okay, so robustness and rapidity, which has analogies to functions of vulnerability and recoverability that I talked about earlier. And then here's another approach that it's essentially, again, another one of these triangular kind of figures that lets your mind wander with not strict linear degradation and recovery, as we generally showed in that first plot, and that the resilience triangle also shows, but gives you a little insight into, hey, what if this recovery, what if these plots aren't exactly linear? And then shows different sorts of degradation, different shapes associated with recovery, and so on, and provide some different definitions to what those restoration and recovery shapes might look like. So we're going to wrap up here pretty soon in this first lecture. Just wanted to let you know about what's going to transpire throughout the semester. So we're going to have a few lectures like what I'm doing today on a few topics that are a little more class related, a little more typical lectures. And we're also going to have several guests that will enrich the course. We'll give you a little bit of an idea about some of the current research topics, current and ongoing research topics in the field. And we're going to describe those in terms of the three interdependent networks that we saw before. So for infrastructure networks, those physical lifelines, we have a couple of speakers, Olafemi Onatamo and Hiba Baru. They'll be giving some lectures, or a lecture each, on infrastructure networks. Then with respect to the impacts on the community, we'll hear from a couple of folks that are collaborators on the CRISP grant. Okay. And then finally, service networks that are engaged after the disruption. We'll hear from a couple of other folks on modeling. And again, for all of these that you're seeing here, we could be talking about descriptive analytics, predictive analytics, and prescriptive analytics. In particular, with service networks, how do we model and optimize performance of service networks that engage after a disruption? Okay, so we've got these three interdependent infrastructure networks, community networks, and service networks. And then spanning all of these networks are some general topics that'll be provided by these three folks, Enrico Zio, James Lambert, and Alex Gates. Okay, that'll be describing various topics that might be more methodological in nature that could be applied to any of these three networks. Okay. With respect to the lectures, some of the material dealing with networks is going to be derived from this book by Albert Laszlo Barabasi called Network Science. You can buy the hardbound version if you'd like. Written in, or came out in 2016. It's an excellent book, very colorful and pretty book. You can also get a lot of that material on his website. Okay, if you buy the book version, the presentation is a little more complete, a little clearer, but a lot of that same material is located on his site if you'd like to see that instead. Okay, and so that's the end of the first lecture. We'll be hearing from some of our guests and from Andres Gonzalez in upcoming lectures. And I hope you enjoy the rest of the semester.